Okay, finding the distance from the origin. We're on 1.9, and this is the second video of it. It says, example 5 says, here is a famous problem from calculus. Let's explore a point, P, x, y, on the graph of y equals x squared minus 1. Our goal is to find an approximation of a point on the graph that is closest to the origin. A says, express the distance d from point P to the origin as a function of x. Alright, so let's remember our distance formula. So we're after the distance. So distance is equal to the square root of y2 minus y1 squared plus x2 minus x1 squared. And they gave us two ordered pairs. They gave us the origin. So let's let this be x1, y1. And they gave us point P, that is x and y. So let's make that x2, y2. Alright, so let's plug in what we've got in here in our distance formula. So the distance is equal to the square root of y minus 0 squared plus x minus 0 squared. Well, we can simplify that. That's just the square root of y minus 0 is y squared plus x minus 0 is x squared. Now, we got that simplified, but it says here to express the distance d from P to the origin as a function of x, meaning x is the only variable that we want in our equation. So what do I know about y or y squared? Well, I know that y is equal to x squared minus 1. So I can substitute that in. So d is equal to the square root of, instead of y, I'm going to put that x squared minus 1. Then I've got the squared plus x squared. And we can work that out if we want to. We don't really have to. So I'm just going to stop here. Now B says use a graphing utility to graph the function for x is greater than 0. Alright, so we're going to put that equation into our y equals. So let's do that. So I got the square root of x squared minus 1 squared plus x squared. Now when I go to hit graph, I'm going to move this up now. Wrong button. Okay, so when I go to hit graph, I do not see what they have on the other side there, okay? So let me see. So when I do graph mine, what I see is this graph where it kind of comes down like this, and it kind of levels out, and then it goes back up. With this, let's say, is my x-axis, and this could be my y-axis. I'm sorry, I said backward. The first one I drew was my y-axis, the second one was my x-axis. Okay, so, but it says we're only looking for x is greater than or equal to 0, so I don't need the rest of that graph. So, but if you notice, it looks like there might be a little wave going on here in the middle. So I need to be able to zoom in a little bit more on that. So what I'm going to do is, first thing is I'm going to go to my window, and I'm going to change my x minimum to 0, because we said we only wanted to see x's that were greater than or equal to 0. And I'm going to go back to my graph. And there I can kind of see, it looks like when it graphed it, it looks like it went down just a hair and then it went up. Now, if I need to see it even closer, I can change my window. I could set my x max to be like 5. So check that out. And I don't really need any of the negative y's because everything's above. So set your y min to 0. Alright, so what I have right now for my table is my x minimum, I put at 0. My x max, I put at 5. My y min is at 0, and I left my y max at 10. So when I go to graph this now, yeah, I can tell that it looks like it dips down before it starts going up on that long stretch. So what we're going to do then is we need to find that minimum value. So we're going to use our calculator to find it for us. We're going to go to second, trace, And number 3 says minimum. So we're going to choose that. Now, on my calculator, it says left bound. So I want to be to the left of that minimum value. So I'm going to take my cursor and I'm going to go over there to basically where x is 0. So I'm moving my cursor over somewhere over here. And that's going to be my left bound. So I'm going to hit enter. And I notice right above there, it puts a little arrow facing to the right. Now it says right bound, so I want to make sure I'm on the right of it. So I'm going to go way over to where I'm going on that upward curve, because I want it to obviously be to the right of it. So I'm going to come somewhere like up in here. This is my right bound, and I'm going to hit enter. And when you do, you're going to see it's going to give you a little arrow facing to the left. If you have the newer calculators, it actually has a dashed line coming down each of those arrows. If you have an older one, you don't see that. But what it's saying is our minimum value then has to be somewhere between those two arrows. And I believe it is, so we don't care about guess, so hit enter. And you'll see it says minimum, and it tells us that's at 0.707, when I rounded 3, comma 0.866. So there's the minimum point there. Now, the problem says to find the values of x where d is a local minimum. We did that. This will give you the points on the graph of y equals x squared minus 1 closest to the origin. Okay, now you got to remember this is a quadratic and it has symmetry. So if we have, I'm going to go back up to my first graph that I kind of scribbled the left side out. If I have a minimum right here at 0.707, due to symmetry, I also have a minimum over here at negative 0.707, 0.866. Now, this is the minimum using my distance formula, but my x's are going to be the same on it. So if I know the x value, how would I find the y value? Well, if I know that x is the negative 0.707, I can plug it into that equation to find its y value. And so let's do that. And we got negative 0.5. So that means that the ordered pair, negative 0.707, comma, negative 0.5, is one of the one of the closest points to the origin. And then we also know that if x is equal to positive 0.707, we can find its y value, which because of symmetry, they should have the same y value, and they do. When we calculate that, we get negative 0.5. So in my other point, 0.707, comma, negative 0.5. These are the closest points to the origin. Alright, so moving right along here, finding a model and solving. So it says the grain is leaking through a hole in a storage bin at a constant rate of 6 cubic inches per minute. The grain forms a cone-shaped pile on the ground below. As it grows, the height of the cone always remains equal to its radius. If the cone is 2 feet tall now, how tall will it be in 1 hour? Alright, well, let's see. We can see that the grain is leaking through a hole in a storage bin at a constant rate of 6 cubic inches per minute. Alright, so we have this rate of leakage. So the rate is 6 cubic inches per minute. What else do we know? The grain forms a cone-shaped pile on the ground below. Okay, as it grows, the height of the cone always remains equal to the radius. So the height will equal the radius. The cone is 2 feet tall now. So the height of now is 2 feet. Now, I see that my rate is in inches and my height is in feet. I have a feeling we're going to have to do conversion in a few minutes here. How tall will it be in 1 hour? Well, when I see that inches cubed, I'm also thinking volume, because I know that's in cubic units. So the volume of that cone shape there is V equals 1/3 pi r squared h. Now, let's see. We know h is equal to r, so we could change either h to r, r to h, whichever. We know the height now. Well, if I know the height now, I can find the volume of right now. And that'll help me. Then I can add in that rate. Okay, so let's try that. So let's see. Now I am going to need to convert. So 2 feet is 24 inches for my height. And remember, my height is equal to the radius. So this is saying V equals 1/3 pi. This is h squared times h. Since the height and the radius are equal. So V is equal to 1/3 pi h cubed. So my volume right now would be 1/3 pi 24 cubed, because that's the height. That 2 feet is 24 inches. And so we can find the volume right now. So the volume right now would be 1/3 pi times 24 cubed. And so I got 14,476.459 inches cubed. Okay, so that's my volume right now. But I know that it's increasing by 6 inches per minute. So what's that volume increase in the next hour then? Because I need the height 1 hour from now. So I need to find the volume 1 hour from now, and maybe I can backtrack and find my height. Well, in 1 hour, a volume is increasing by 6 inches per minute. Well, how many minutes are there? There's 60 minutes in an hour, so that means by 360 inches cubed. All right, so we got our volume right now and our volume of increase in 1 hour, and that's going to give us our total volume. All right, so our volume right now was a 14,476.459, and our volume of increase there was 360. So when we add those together, we get 14,836.459. Well, let's see then. Remember, we know from this equation right here that the volume is equal to 1/3 pi h cubed. So 1/3 pi h cubed. Well, if my volume is 14,836.459 equals 1/3 pi h cubed, can we solve for h? We can. First, let's get rid of that fraction by multiplying by its denominator. So, 3. What we do to one side, we have to do to the other. So, I have 44509.377 equals pi h cubed. Then we're going to divide by pi. I'm running out of room here. And so we'll end up with h cubed equals 14,167.775. And then to get rid of the cube, we're going to take the cube root. So the cube and the cube root cancel, so we get h equals. Now in the calculator here, if you go under math, you'll see that number 4 says the cube root. And then you can grab your answer, or type your answer in if you prefer. And we get 24.197 inches. And so that is going to be our height in 1 hour.